Let's look at cylinder blocks. The cylinder block is the largest part of the engine. Its upper section carries the cylinders and pistons. Normally, the lower section forms the crankcase and supports the crankshaft. It can be cast in one piece from grey iron, or it can be alloyed with other metals like nickel or chromium. The iron casting process begins by making up the shapes of what will become water jackets and cylinders as sand cores, which are fitted into moulds. This stops these parts becoming solid iron during casting. Molten iron is poured into sand moulds that are formed by patterns in the shape of the block. After casting, core sand is removed through holes in the sides and ends, leaving spaces for the cooling and lubricant passages. These holes are sealed with core or Welsh plugs. The casting is then machined. Cylinders are bored and finished, surfaces smoothed, holes drilled and threads cut. All cylinder blocks are made with ribs, webs and fillets to provide rigidity, but also to keep weight to a minimum. As more manufacturers try to make vehicles lighter and more fuel efficient, more and more engine blocks are being cast from aluminium. A block made of aluminium alloy is lighter than if it were made of cast iron. So if two engines are generating the same power, the alloy version would have a better weight-to-power ratio than the cast iron version. Aluminium alloy blocks are made by various casting processes, including pressure casting. Another method is gravity casting, where the molten metal is poured into moulds. Cast iron liners are usually used in the cylinders of aluminium blocks, and sometimes in cast iron blocks. Some sleeves are cast into the block. Grooves on the outside form a key that stops any movement in the cylinder. They also increase the surface area to assist heat transfer from the sleeve to the block. Some blocks don't need liners. They can be made of wear-resistant material that makes a hard-wearing surface for the pistons and piston rings. Or the cylinder bore may have some sort of surface treatment to make it hard-wearing. When the cylinders, block and crankcase are all cast together, it's called a monoblock construction. This is called a horizontally opposed block. It has a split crankcase. The two engine blocks are joined together by the flanges of the crankcase. In air-cooled engines, the cylinders are usually made as separate parts, then bolted to the same crankcase. Each cylinder has cooling fins. They're often machined to give uniform thickness and allow free flow of air. Let's look at cylinder sleeves. Cylinder sleeves are used in engine blocks to provide a hard-wearing material for pistons and piston rings. The block can be made of one kind of iron that's light and easy to cast, while the sleeve uses another kind that is better able to stand up to wear and tear. There are three main types of sleeves: dry, flanged dry, and wet. The dry sleeve can be cast in or pressed into a new block, or used to recondition badly worn or damaged cylinders that can't easily be rebored. It's a pressed fit in its bore in the cylinder block. Its wall is about 2 millimetres thick. Its outer surface is in contact with the block for its full length. Its top finishes flush with the top of the block and can hardly be seen. Once in place, dry sleeves become a permanent part of the cylinder block. A flanged dry sleeve is like a normal dry sleeve, but a flange at the top fits into a recess in the surface of the engine block. It's not a tight fit, and it can be replaced if it's worn. With a wet sleeve, the outer surface is part of the water jacket around the cylinder. It's called wet because it has coolant against its outer surface. This helps speed up heat transfer between the sleeve and coolant. The sleeve is sealed at the top to prevent coolant leaks. This stops coolant entering the combustion chamber and the bottom of the crankcase. A flange at the top of the sleeve fits into a recess in the block. The lower end has 1 or 2 neoprene sealing rings. With coolant in direct contact with the cylinder sleeve, corrosion can be a problem. It can even insulate the sleeve from the coolant, which reduces the main advantage of having a wet sleeve at all. The walls on wet sleeves are thicker than on dry sleeves. They don't have the same support from the block as dry sleeves, so they depend on their wall thickness to stop distortion. In diesel engines, vibration caused by combustion can cause cavitation. This damage appears similar to corrosion, and it can eventually destroy the cylinder. This section examines cylinder heads. The cylinder head bolts onto the top of the cylinder block where it forms the top of the combustion chamber. Inline engines of light vehicles have just one cylinder head for all the cylinders. Larger inline engines can have 2 or more. V-type and horizontally opposed engines have a separate cylinder head for each bank of cylinders. Just as with engine blocks, cylinder heads can be made of cast iron or aluminium alloy. A head made of aluminium alloy is lighter than if it were made of cast iron. Aluminium also conducts heat away more quickly than iron. So with an aluminium alloy head, the heat of combustion can be conducted away into the coolant more quickly. Manufacturing the head is similar to manufacturing the block. A casting mould is made. Sand cores are put in to form any hollow areas. Depending on the engine, these can be for coolant and lubricant passages and inlet and exhaust ports. Air-cooled engines have cooling fins cast into the cylinder head. The underside of the head is shaped to form the combustion chamber. Molten metal is poured in and allowed to cool. The cores are broken out and removed, and the cylinder head cleaned of any sand. After casting comes machining. Surfaces that must seal are machined flat. Holes are drilled and tapped for attaching bolts and studs. In sand cast heads, the large holes that had contained sand are machined, then fitted with soft metal plugs called core plugs. Cylinder heads are designed to help improve the swirl or turbulence of the air-fuel mixture and prevent fuel droplets settling on the surfaces of the combustion chamber or cylinder walls. When air-fuel mixture is compressed between the piston and the flat part of the cylinder head, it produces what's called squish. That means squeezing of the gases to increase their velocity and turbulence. In petrol engines, the 3 most popular combustion chamber designs are called hemispherical or pent roof, bathtub, and wedge. This is the hemispherical or pent roof combustion chamber. It has the intake valve on one side of the chamber and the exhaust valve on the other. This provides cross-flow. Air-fuel mixture enters on one side and exhaust gases exit on the other. Positioning the valves in this way leaves room for relatively large valves and ports, and that helps the engine breathe. Breathing refers to the engine taking in the air or air-fuel mixture. Fuel starts to burn at the plug. Then burning travels outward in all directions. This is called flame propagation. With the plug in the middle of the hemisphere, the flame front has less distance to travel than in some other designs. This gives rapid and effective combustion. This design is common in a lot of passenger vehicles. The bathtub combustion chamber is oval-shaped, like an inverted bathtub. Valves are mounted vertically and side by side, making them simple to operate. The plug is to one side, and that creates a short flame path. It all helps increase turbulence. The wedge-shaped combustion chamber tapers away from the plug, which is at the thick end of the wedge. The valves are in line and inclined from the vertical. This design usually has a smaller surface area than the others, with less area where fuel droplets can condense. Less fuel is left unburned after combustion, which reduces hydrocarbon exhaust emissions. And since the flame is directed towards the small end of the wedge, damage caused by detonation is reduced. The size of passages in the head can affect engine output. Smaller intake and exhaust passages and ports allow more torque at low engine speeds. This is because smaller passages improve mixing of air and fuel at low speeds, which causes more efficient combustion. At higher speeds, however, these smaller passages restrict airflow. To reduce the effect of this engine has two inlet valves. One opens at low speed and the other operates at higher engine speeds. Larger passages produce greater power at high engine speeds. Each intake and exhaust passage can be formed separately in the head. Intake passages for adjacent passages may have a common thin wall between them. This is called Siamesed. Exhaust ports in the same head can also be Siamesed. When all intake and exhaust ports are on one side, it's called a counterflow head. They can be cast separately or Siamesed. When all of the intake ports are on one side and exhaust ports are on the other, it's called a crossflow head. This allows for straighter passageways and higher efficiency. Diesel combustion chambers come in two main types, direct and indirect injection. Both are designed to promote turbulence, to help the compressed air and injected fuel mix well. Engines using direct injection have cylinder heads with a flat face. The combustion chamber is formed in the top of the piston. Sometimes the rim of the piston provides squish, forcing the air to the centre of the combustion chamber. This causes turbulence as fuel is injected into the cylinder. In indirect injection, the piston is fairly flat or has a shallow cavity. The main combustion chamber is between the cylinder head and the top of the piston, but a smaller separate chamber is in the head. Fuel is injected into this smaller chamber. It can have various designs. This is a swirl chamber. It's spherical and connected to the main chamber by an angled passage. Both the injector and glow plug are screwed into the head. The glow plug preheats the air inside to help start the engine. During compression, the spherical shape makes the air swirl in the chamber. This helps make a better mixture of the air and fuel, which improves combustion. This combustion chamber is divided into a main combustion chamber and an air cell joined by a throat. The injector is in the throat. When injection commences, combustion pressure forces the air to flow from the air cell, where it mixes with fuel from the injector. The rush of air from the air cell produces a rotary motion of gas in the main chamber, which helps make combustion more efficient. This pre-combustion chamber is screwed into the cylinder head. The injector is mounted in the upper end. Injection occurs near the top of the compression stroke. Only part of the fuel is burned in the pre-combustion chamber because of the limited amount of air there. The high rise in pressure forces burning fuel into the main chamber. This happens very rapidly, which helps make more efficient combustion.
Turbulence refers to the swirling motion of a liquid or a gas. It helps to maximize the mixing of air and fuel, which helps make sure the combustion process occurs efficiently. Without turbulence, the air-fuel mixture can form local areas of high pressure and temperature that can cause detonation during combustion. A high level of turbulence can prevent this. Grey iron is a form of cast iron. There are many different kinds of cast iron depending on the particular materials they contain. Grey iron is a cast iron that contains carbon in the form of graphite, plus silicon, manganese and phosphorus. The fractured surface of a cast iron with graphite appears grey, hence the name. It is brittle and cannot absorb shocks. It resists heat and corrosion and can be cast into many different shapes. It is used for many components.
Head gaskets seal and contain the pressures of combustion within the engine between the cylinder head and block. They also seal oil passages between block and head, and control the flow of coolant between the block and the head. Some gaskets provide or adjust clearances. Some joints between surfaces on modern engines are being sealed with special sealants which eliminate the use of gaskets in some applications. Gaskets around a rotating part would quickly wear out and leak. To seal these parts, oil seals are needed. Many different kinds have been developed. The most widely used is the lip-type dynamic oil seal. It has a shaped dynamic rubber lip that's held in contact with the shaft to be sealed by a circular coil spring called a garter spring. A similar sealing principle is used to seal the valve stem to prevent oil entering the engine combustion chamber. Rotating or sliding shafts can also be sealed by using O-rings, but generally they're not as durable in most applications as the lip-type seal. As a general rule, oil seals must be replaced when a component is overhauled.